A cantilever beam of 5 meter span is 240 by 600 mm in section. It is pre-stressed with effective pre-stressing force of 600 kN, which is located at a constant distance of 100 mm from the tension edge. Determine the maximum UDL the beam can carry in addition to its own weight. Also, determine maximum compressive stress developed in concrete under this load. Concrete weighs 25 kilonewton per meter cube. So firstly we need to understand that the given problem is cantilever. So if it is a cantilever beam, the behavior of the beam is totally different to that of the simply supported beam. In the case of the simply supported beam, the tension will be acting at the bottom edge and the compression will be acting at the top edge. However, in the case of cantilever, tension will be acting at the top and the compression will be acting at the bottom. So you have to read the statement carefully and the expressions to compute the stress resultant also changes here. Everything changes. We need to take stock of all these things carefully. Then problem needs to be solved. So let us draw the sketch carefully. So in the figure statement, it is given that it is carrying an effective prestressing force of 600 kilonewton, which is located at a constant distance of 100 mm from the tension edge. So tension is acting at the bottom. Sorry, tension is acting at the top. So here we need to draw, this is the cable. You have to measure 100 mm, plot it, and then eccentricity is always calculated with respect to the neutral axis. The total depth is 300, 600. 600 divided by 2 is 300. So 300 minus 100, finally we get the eccentricity as 200. Then neatly plot the longitudinal section of the cantilever beam. We need to find out what is this UDL it can carry for the given condition. Next, so all the preliminary calculation needs to be done here. P is given in the data. Since it is a rectangular section, area is 240 by 600. Eccentricity is computed, and section modulus and moment of inertia can be calculated with the conventional formulas. And then self weight of the beam is given by area into density. And next, bending moment at the central span. Since it is a cantilever beam, the bending moment at the central span, or the maximum bending moment, is given by WL square by 2. Here in this cantilever beam, the bending moment is maximum always at the support condition. So this is the support, the other end is totally free. So the bending moment is maximum at the support and it is given by WL square by 2. Whereas in the case of simply supported beam, the bending moment is maximum at the central span. So we need to be careful in this concept and even the formulas as well. And also here, and one more important condition, what is specified here is that you have to determine the maximum compressive stress developed in the concrete under this load. So which means where the compression stress is expressed here, expected here, the compressive stress is expected at the bottom here. Okay, and here one more thing is that we need to find out first what is F superior, because the load is also unknown here. Since the load is unknown here, you cannot find out the compressive stress by directly applying the F wherever the compression is acting, that is at the bottom. So here we need to make use of the fundamental aspects of pre-stressed concrete. That is, the main aim of the PSC is always to nullify the tension, that is tension has to be zero. So where the tension is zero here, tension is acting at the topmost fiber in the case of cantilever. Therefore, at the top, which means F superior needs to be equated into 0 here. See, the major change here is that there is a change even in the expression, as well as this expression is quite different from that of the expression used for the simply supported condition. Since here a load value is also unknown, we directly cannot compute what is the compressive stress, and thereby we are making use of the fundamental concept of pre-stress concrete. That is, we need to nullify the tension, which means we need to equate a resultant stress expression with reference to the tension h into 0. So in the case of cantilever, tension is acting at the top, compression is acting at the bottom, therefore f superior is made equal to 0. And then substitute everything, finally we get the answer for mq. And again we can apply the expression, bending moment expression, wl square by 2, and rearranging and solving we get the dead load value as, sorry, live load value as 10.8. And with this obtained live load value, you can write down an expression for f inferior, and then we can directly find out what is the compressive stress developed.